Thank you everybody for coming to this What Is talk on latent class analysis. I'm Tarani Chandola, based in social statistics and CCSR. Just want to start off by saying the term latent class analysis is very similar to other kinds of methods that you hear about in the literature, like mixture modeling or finite mixture modeling, latent profile analysis. These are all very similar kinds of modeling processes, and I'll illustrate the commonalities and sort of the differences between these kinds of modelings, these kind of models in the lecture today. To start off with, perhaps let's start off with something slightly more familiar, which is factor analysis. Latent class analysis is very similar to factor analysis. But with latent class analysis, what happens is that you have categorical response variables as well as categorical exogenous variables, categorical latent variables. Before I go any further, how many of you are familiar with factor analysis? Great. And how many not so familiar with factor analysis? Okay, a few not so familiar with factor analysis. Okay, I'll go through some of the basics of factor analysis because that helps with the building blocks of latent class analysis. I just want to say, to start off, that latent class analysis is similar to factor analysis. It's about finding out about the complex pattern of association between different sets of variables. So over here we've got four sets of variables, and factor analysis is about trying to find out what are the intercorrelations between these variables. So these are slides that next few slides are taken from my factor analysis introduction class, which is about, well, we have two variables, x and y, and say we observe a correlation between x and y, x and y are related somehow. We can either try to think about this correlation in terms of x being a cause of y, or y being a cause of x, or in terms of an unmeasured third cause, z, for example, that is causing both x and y, and that is causing the apparent association, the apparent correlation between x and y. So it's not really x causing y or y causing x. It's some unmeasured cause that is causing both to appear to be correlated. And this is a factor analysis situation when you've got some unmeasured, unknown, latent variable that is causing apparent correlations between variables. Now, in the social sciences, these kinds of unmeasured things, unmeasured constructs, latent concepts are very, very common. Things like, got an example here of social capital. It's very hard to observe social capital. How do you go out and count social capital on the streets? How do you ask people about social capital? You infer social capital only indirectly. You can't observe it directly. You only infer it indirectly through things like membership of groups or organizations, or what kinds of newspapers people read. And those are the things that you can observe. And through observing the correlations between these kinds of variables, you infer that there is an underlying construct that you can't measure, but which is associated with this social capital. Prejudice, for example, is another typical thing that it's very hard to observe directly, but you can observe it indirectly through housing segregation or intermarriage patterns. So what happens in a factor model is that we start off with correlations between our observed variables. We've got 4 observed variables, and this is a typical correlation matrix over here. But in a factor model, what happens is that we take away the correlations between y1, y2, y3, y4. We take away all these intercorrelations and say that those are not important. What's important is this unmeasured, unobserved f, this factor that is causing these intercorrelations between y1, y2, y3, y4. Now, this might sound a little bit abstract, but let me give you a concrete example over here. say we've got four survey questions, typical survey questions. People are asked, I often feel blue, I dislike myself, I have a low opinion of myself, and my life lacks direction. People who tend to score high on the first question will tend to score high on all the other questions. So you will expect some strong correlations between these observed variables. What's the underlying latent variable here? Depression, yeah, depressive symptoms or depression. So it could be that actually it's not the correlations that are particularly interesting. It's not the intercorrelations between these observed variables that are telling us anything. Actually, what we're interested in is whether there is an underlying construct, like depression, that is causing the apparent intercorrelations. And so that's what factor analysis does. It estimates these, to what extent there is this underlying factor that is causing these apparent intercorrelations, and it estimates sort of the weights, how much of this underlying depression is explaining each of these observed variables. In terms of concrete numbers, this is our typical sort of taken from a spreadsheet where we've got 4 responses, people who score 0.8 on the first scale, 1.4 on the second scale, minus 0.3 on the third scale, minus 0.2 on the fourth scale. We want to find some way of representing the factor score. And so what the factor score is simply a number. It's not a mysterious process. Some people think that because I can't observe this, that means it's something really mysterious. I don't understand what it is. What it is, what that factor score, it's a number. Here we've got 1.2. If we add 1.2 to the errors for the first variable, sorry, I didn't show you the error terms over here. I mean, this factor score, this depressive symptoms factor, does not explain all of the variance in each of these items. There will still be some unexplained errors for each of these items that is not explained by the single underlying factor of depressive scores. So each of these observed variables will have some error terms associated with it. Say we've got the first factor score here, and it's got some an error term for the first variable of minus 0.4. So 1.2 plus minus 0.4 gives you the observed the observed characteristic of 0.8 for the first indicator. Similarly, 1.2 plus 0.2 gives you 1.4 for the second indicator. Some of you might be thinking, well, why don't I just take an average? Y1 to Y4. Take a mean, for example, from Y1 to Y4. Is that doable? Why is that the same thing as calculating a factor score and the error terms for each indicator? Is what I'm doing over here, 1.2 plus minus 0.4 and getting a value of 0.8. Is that the same as taking an average mean for each of these indicators? Depends on the indicators. In what way?
The type of data they are
They're categorical. Okay, so over here I'm making the assumption that my indicators are continuous, that they are,
They don't know how much weight each of them.
How much weight? Yes, that's right. So that's the key thing. We don't know how much weight. If I take an average, I'm assuming that each of these weights over here, these factor weights, are equal. 25% for each of these weights. That's what I'm assuming. If I just take if I just average out Y1 to Y4. But actually, in a factor analysis, it might be that actually these two items, I often feel blue and I dislike myself, are much more strongly correlated to each other than Y3 and Y4. So what a factor analysis does is it takes into account the fact that some of these items are more strongly correlated with each other, and it assigns a higher factor weight to it than other indicators. And in a factor analysis, it's very easy to get a model fit, which is what you what you observe in terms of the observed variances and covariances, as well as the expected fit from your model. And you can do a Pearson chi-square test to see to what extent your model of depressive symptoms over here is a good explanation of the intercorrelations between Y1 to Y4. And you can calculate chi-square test to see whether or not it's significantly different from zero. If it's significantly different from zero, one of the basic arguments is that's not a good model. Okay, so that's all about factor analysis. Latent class analysis is very similar to factor analysis. The big difference is that instead of an underlying dimension that is continuous, over here in this example, I was assuming that depression or depressive symptoms represents an underlying continuous dimension. I can count it, from 0 to 100. Say it represents a scale from 0 to 100. But actually, in depression, very often people are more interested in whether or not people are depressed or not. They're not interested in an underlying continuous scale. They're interested in classes, in categories. Are you depressed or not? What makes one person more likely to be in a depressed class versus another person? So we're interested in finding out the underlying latent classes, not latent dimensions, not latent continuous dimensions. If you're interested in a single latent continuous dimension or two latent continuous dimensions, we will do factor analysis. And latent class analysis, we're interested in the underlying categories or classes, discrete categories. This is also very common in social sciences, also in the health sciences. There are often no gold standards for classifying a set of responses into yes, this person is depressed, no, this person is not depressed. Based on people's answers to survey questionnaires, it's very hard to know what is the cutoff point. If a person scores 10 or more on this questionnaire, is this person really depressed, or maybe the cutoff is 11, maybe the cutoff is 9. You actually don't know. And this is where latent class analysis is really useful. It's really useful to classify people into groups when you don't have a gold standard, when you don't have this cutoff point for classifying people into these depressed or not depressed latent categories. So what latent class analysis does is it predicts latent class memberships such that the intercorrelations between these variables are no longer exist. That these observed variables are independent given the latent class membership. This is also it's conditional independence. This is also a characteristic of factor analysis. The factor analysis, like we did over here, is one in which there are no residual correlations between these observed items once we take into account this underlying factor. And it's exactly the same assumption that we make for latent class analysis, that once we classify people into these two or more classes, there are no more correlations between each of these each of these observed variables, each of these items. What the latent class estimates, what they actually provide us, is it gives us the prevalences in each of these latent classes. So how many people are classified into this class, how many people are classified into the other class, that's what it gives us. It also gives us the conditional probabilities. So what's the probability of scoring high on the feeling blue questionnaire if you're in class 1? What's the probability of scoring high on the feeling blue question if you're in the not depressed class? So these conditional probabilities are also a result of latent class analysis. So the two key things that a latent class analysis does, it gives us how many people there are in each of these groups, and also the conditional probability of scoring high on each of these observed items given your membership of the class. So what what's the raw data with which we use to fit these latent class analysis? Well, it's a contingency table, like contingency tables that you're all familiar with. Here we've got the 4 observed variables: feeling blue, having a low opinion of myself, I dislike myself, and my life lacks direction. Here, I'm assuming that these are just binary indicators. So somebody that scores 0 is not feeling blue. Somebody that scores 1 is feeling blue. So they're binary indicators. And I simply count up the number of people in my sample that have these 4 characteristics of 0 on each of these indicators. Similarly, I use a count of the number of people in my sample that have that scores 0 on these 3 characteristics and scores 1 on my life lacks direction. So we can easily count up the number of people in all possible combinations of these 4 categories. And having done that, what latent class analysis is that it gives us this extra column over here, which is how many people it expects to be in latent class 1 or in latent class 2, given these sets of observed characteristics. So over here, after doing the latent class analysis, it gives me, well, for this particular combination of observed characteristics of 4 zeros on each of these characteristics, I find that I expect to be, given my model, there are only 9 people in latent class 1, which means that given that there are 15 people in total in this, with these characteristics in the data, I expect there will be 6 people in latent class 2. Similarly, for these combination of characteristics where I've got 0 on the first 3 observed characteristics and 1 on my life lacks direction, my model estimates that I expect 6 people in latent class 2, the not depressed category, which means that given that there are 14 in total on my observed data, there will be 8 people in latent class 1. I expect there to be 8 people in latent class 1. So that's what latent class analysis does, basically. It converts this contingency table, this unconditional contingency table, into a conditional contingency table, whereby it adds this extra column of membership into either latent class 1 or latent class 2 or more latent classes, and it gives you the numbers it expects to be in each of these latent classes. Now, how does it do that? Okay, that's where all the statistics comes in, and I'm not going to go into that because it's quite hard to do that in an introductory talk. Plus, I'm not really the right person to talk about the process by which whatever statistical package you use, it arrives at calculating the numbers it expects to be in each of these latent classes. But just a quick, a couple slides on that. The approach it basically uses is maximum likelihood estimation, but it is complex because your latent class membership is unobserved. The likelihood function is complex. Now, what most software packages do is that it takes a maximum likelihood approach and it uses the expectation EML algorithm, expectation maximization algorithm to calculate what it predicts to be in either latent classes 1 or 2. Firstly, it starts with the maximization step. It produces what it expects the maximum likelihood estimates. What are these estimates? These are the prevalences in each of the latent classes and the conditional probabilities. So the 2 things that I said latent class analysis does, the prevalences, the estimates for how much it expects, how many people it expects to be in each of the classes, as well as conditional probabilities of scoring high on each of the items, given latent class membership 1 or 2. So it produces this maximum likelihood estimates from the complete table. The expectation step is that it uses these parameter estimates for prevalences and conditional probabilities to give us what the expected values given those estimates are, and then tries to improve the fit of the model by getting the expected numbers in each of the tables to be as close as possible to the observed contingency table that you have. So it's an iterative process it undergoes. The key thing is that actually for the first step, all software packages, what they tend to do is to provide random estimates because it doesn't have any information on what it is like, what the likely population prevalences of each of these latent classes are. It doesn't have any estimates on what the conditional probabilities are. So the first step is actually sort of randomly allocates people into different classes, and so there's a random first step. But having done that, it sort of goes through this iterative process to try to give you a best fitting model. So I said I'll go through some of the slight differences but commonalities between these different kinds of models, like mixture models and latent class analysis. Latent class analysis tends to be, what I described tends to be one where we've got categorical outcomes. So usually, our outcome data are binary, like in the example that I just had. So the observed indicators, I'm feeling blue, yes or no. I feel tired all the time, yes or no. These are binary indicators. Where our observed indicators are not binary, but continuous, we use either mixture modeling or latent profile analysis. Mixture modeling is used when we've got, we tend to have only a single outcome. So over here, say we've got a distribution of a continuous variable. I'm going to say this is, say, the distribution of body mass index. It's not a normal distribution. You see straight away, we've got this red line with this hump at the right-hand side. It's not a normal distribution, but it seems to be composed of two normal distributions. There's a distribution in the light green over here, where you've got a mean of say, body mass index that is much lower than a smaller group that is shifted to the right, so that it has a higher body mass index. It has a higher levels of obesity. You can see immediately that if we do something like a latent class analysis, but for continuous variables, we could be estimating two unobserved classes of the distribution of body mass index, two unobserved distributions where we're trying to estimate what is the mean and variance of the first group and what is the mean and variance of the second group, and as well as how many people there are in each of these groups. So it's exactly similar to what latent class analysis, what we're trying to do in latent class analysis, which is trying to estimate what are the prevalences in each of these groups, as well as what is the conditional probabilities of scoring high on each of the indicators given your latent class. Mixture modeling process is simply a latent class analysis where you've only got one outcome variable, and that outcome variable is continuously distributed. You don't have to restrict yourself to one outcome variable. You can do a latent profile analysis where you've got multiple outcome variables, like in latent class analysis, like that we did, but each of these is continuous rather than categorical. So that's the only difference between all these different terms for models. They're highly similar, and fitting them in statistical models, in modeling packages, you get very similar looking terms in the outcomes. I'm just going to show you a series of models that are fitted for body mass index and take you through some examples of what are the outputs you get when you do this kind of mixture modeling. Over here, so I've only got a single outcome, body mass index, and that's the distribution I have in my population. I see it's not a normal distribution. It is quite skewed. It's got a fairly long tail over here. So when I looked at this data, I thought, well, maybe there isn't a single underlying class over here. Maybe it's a combination of two latent classes over here. But I didn't know what the cutoff was. I couldn't say for sure that whether one class was this, another class was this. So I do a mixture modeling process to see, what are the cutoffs for each of these classes. That's the mean in the overall population, 25.6. So it's slightly overweight. People who are familiar with body mass index knows that if you score 25 and over, you're overweight with a variance of 15.3. So that's easy to get from descriptive statistics. What latent class analysis does is it sort of gives us the distribution of each of the latent classes. Over here, I'm showing you the results from a two-class model. So it gives me the expected distribution in class 1 and class 2. Over here, you see class 2 is extremely skewed, but also it starts with a much higher body mass index. That is a body mass index of 33 over here, whereas for class 1, it ranges from 17 to 30 over here. It's okay, this is not perhaps a great example, but I just wanted to give you a flavor of what the outputs from a latent class analysis or mixture modeling process would look like. It gives you the means and variances for each of the classes. Over here, I'm showing you the results for 3 classes. It gives you the means and variance for each of the classes, as well as the prevalences, how many people it expects to be in each of these classes. That's what a latent class analysis, latent profile analysis, mixture modeling process, those are the typical outcomes that you will get from that. And I just wanted to graphically show you what the software is doing when it's trying to calculate these latent classes. So where we've got a single outcome like body mass index, for example, what the mixture modeling process is trying to do is it's trying to estimate what are the means and variances of the unobserved distributions of the two classes over here. So that's the normal distribution for the whole population. But what the mixture modeling process is doing is trying to estimate, well, what are the unobserved classes that we have over here that have different means and different variances. So you can picture that quite easily for a single outcome variable. It gets quite a lot more difficult when you have 2 or more variables. But this graph is useful in helping us to understand what a latent class analysis is doing when you've got correlations between 2 or more variables. So here we've got a correlation between y1 and y2. So that correlation is represented by this line over here. Say we've got a correlation between y1 and y2, represented by this line over here. What a latent class analysis is doing is it's trying to split up this correlation into groups. Over here, it split up this correlation into 3 equal-sized groups. Doesn't have to do that. It might be that there are only 2 groups and they're not of equal size. It might be there are 3 groups and they're not of equal size. But that's what a latent class analysis is basically doing. It's trying to split up this correlation that you have over here into unobserved groupings and trying to estimate the mean, the variances for each of these groups, prevalences, as well as the conditional probabilities of belonging into, or scoring high on each of these observed indicators given your class membership. The big question in latent class analysis, how many classes do you decide upon? And the problem is, unlike factor analysis, where you can look at the change in chi-square when you add more dimensions to your model. Unlike factor analysis, for latent class analysis, you can't use the chi-square statistic. You can't use the chi-square difference test to say, yeah, actually adding another latent class here improves the fit of the model. We don't have that luxury. So in order to do that, we tend to look at a range of model fit statistics like the log likelihood, the AIC criterion, the BIC criterion, and you'll see in latent class analysis, when people fit more and more latent classes, they tend to produce tables that show a variety of these fit statistics and compare, whether there is a general improvement in fit. When you look at all these different criteria, the entropy measure is also really useful. So it's a measure of model misclassification. But perhaps the single most important thing is examining whether the latent classes make any sense. So it's examining the distribution of the latent classes, the trajectory shapes for these latent classes, and whether you might, in your sample of 1,000 people, maybe you find that there are 3 latent classes, but the third latent class only has 5 people in it. So substantively, okay, statistically it might exist. Substantively, maybe it's not a very interesting class. So whether it makes substantive sense, whether the shapes make any sense. So when I said that we tend to look at a variety of fit statistics, so we tend to look at the log likelihood, whether it's increasing when we fit more classes. Look at the number of parameters, the AIC, BIC statistics. Entropy, we tend to see, if it's closer to 1, that's a good sign. When it dips below 0.8, that's usually slightly problematic. We've got some pseudo likelihood statistics that software can compute that gives you a p-value, but it's not the only statistic that we can use. In fact, if you just rely upon that, that's highly misleading. So you look at a range of these, try and graphically plot these likelihood or AIC, BIC statistic to see where there's the greatest improvement in fit, and then where there's a leveling out and say, well, actually, from this graph, it looks like, well, yes, you improve fit a lot going from 1 to 2, but not much from going from 2 to 3 classes. So that's another way of trying to decide on how many classes that you have. And the reason why we're trying to find out about these latent classes is not because, well, statistically we can, it's because we're finding it inherently useful. We're trying to, I was given the example of who scores high or low in terms of depressive symptoms, who's depressed or not. And we're trying to use that to predict other things. So that latent class is not only causing membership into high or low categories on your observed variables, it is also causing other outcomes. And it's very easy to model that in a latent class analysis. So you can have other dependent variables in your analysis apart from the things that you can have other dependent variables that are predicted by your latent class membership. So in this example of obesity, where I've got a latent class of obese and not obese people, that splits up their BMI distribution. I'm interested in, are the obese people, do the people who get categorized in the latent class that I call obese, do they then develop other kinds of health problems? So I can do this jointly. I don't have to model this separately to get the latent class membership. And once knowing the latent class membership, I then put that into a separate model. I don't have to create separate models. I can just do that all in one step. So it estimates all these parameters jointly. Similarly, in a latent class analysis, not only can I estimate another kind of dependent variable, but I can also estimate what predicts membership into these latent classes. Very often, I'm not just interested in other things that are predicted by my latent classes, but I want to know who gets put into the unobserved category of obese or not obese, or who gets put into the what predicts membership of the depressed or not depressed class. And so very often that's our key research interest. It's not so much what our latent classes predict, but it's what predicts membership of those latent classes. And once again, we can do that all in one step. We can estimate all these parameters, these regression coefficients jointly with the latent class analysis model. So just to wrap up, at a conference I was, I think last year, on sort of latent class analysis type problems. One of the big questions of the conference was, are you a joiner or splitter? Do you tend to look at the world as belonging to a single underlying continuous dimension, or do you look at the world in categorical terms, yes or no, membership of one class, membership of another class? And I just wanted to highlight that actually it's the same question. In a factor, so basically it's people who use factor analysis when looking at questions of unobserved latent variables, and people who use techniques like latent class analysis when looking at unobserved variables. And actually, it's the same thing. A factor analysis, you've got a correlation between different sets of variables. So here we've got the factor over here, represented by this axis, and we've got one of the y variables over here. And we're interested in the correlation between each of these variables. So that's what a factor analysis does. It tries to produce this line over here, which represents the overall correlations between each of these variables. What a latent profile, latent class analysis does is exactly the same thing, but it's trying to split up that correlation into different classes. It's another way at looking at correlation between variables, but it's saying that, well, actually there might be that actually the means and variances of items over here might be different for some groups versus other groups. So it's sort of taking the factor analysis one step further and saying, well, we don't have to assume everybody represented by this correlation over here comes from a single group, that there might be different groups in this correlation over here. So that's basically what a latent class analysis is about. And I just got some resources over here, some really nice frequently asked questions represented over there. Brian Francis did a nice paper for Research Methods Festival that's available from our CCRCL website. There's a list of software that fits latent class analysis. By far the most popular tend to be Latent Gold, M+, the GLAM modules in Stata. So Stata alone doesn't do that, you just have to download the GLAM modules. I've never used GLAM in Stata before. I tend to use M+, but that's quite expensive. There are short courses available that we'll be teaching on. Nick Schrein and I will be teaching the introduction to structural equation modeling, but with a strong emphasis on these categorical, not just categorical outcomes, but these categorical latent classes, as well as there are short courses on latent trait and latent class analysis later on next year by Yoni Kuhan.